Hey math fans, in this video we're going to do some review exercises from chapter 2, starting with problem number 3, which says to simplify the following expressions involving events A, B, and C. So part A is asking you to show what this set is. So I'm going to go ahead and write this as a claim. And my claim is that A union B intersect with B union C is actually going to equal B union A intersect C. This is a result from set theory that essentially compares the intersection and the union to the distributive property, where you're taking B and distributing that to both A intersect C, where the overall structure of the intersection remains the same, but the thing that changes is that you have B union A intersect with B union C. Okay, so of course I'm going to go ahead and prove this claim. And how do we show the equivalence of two sets? Well, you have to show it by double inclusion. So we're going to go ahead and start by letting x be some arbitrary element of the set to the left. So we're going to let x be an element of A union B intersect with B union C. And then we have to show as a result that x is an element of that. And then you have to go the other way around. But actually, everything that I'm going to do is going to be if and only if. So really, I'm just going to prove one direction, and the other direction is pretty much the exact same. Actually, it is the exact same, just in reverse. Okay, so if x is an element of this intersection, that means that x is both an element of A union B and x is an element of B union C. Okay. But this implies the following. It implies four different things could happen. Okay, because x being an element of A union B means that either x is in A or x is in B, and x is in B or x is in C. And I just want to remind you that if x is in A or x is in B, it could be in both. We don't know. Okay, so that is a possibility as well. Okay. Okay, so from this, we have the following four possibilities. Either x is in A and x is in B, or x is in A and x is in B, or x is in B and x is in B, which is really just saying that x is in B, or x is in B and x is in C. Okay, so what that means this is the same as saying what? Well, x is always going to be an element of B for every single one of these cases except the first one. Look at it. X is in B here, here, and here. So either that is true, or x is not in B. But if x is not in B, it must be in A and C. Okay, but this is the same as x is in B or x is in the intersection of A and C. And finally, we have what we want, which is that x is in the union of B and A intersect C. And you can go the other way around as well and show that if x is an element of here, then you could just keep going back up until you show that it has to be an element of that. Okay, but that's just a result, and that's essentially going to be the answer. Okay, so that's our answer. The reason why that's so important for me to go through is because we're just going to use that on parts B and C. Okay. All right, so let's do the same thing on part B. So part B asks to simplify this set. We have A union B intersect with A union B complement. Okay, but equivalently, we can kind of factor the A out in a sense. And as long as we keep the overall structure, we should be okay. So this should be the same as A union B intersect B complement by the above, right? It's just now we're replacing C with B complement. But it's the same idea. Okay, and what is the intersection between B and B complement? Well, by definition, they're mutually exclusive, so they have nothing in common. So this is really the same as saying A union the empty set. So either an element is in A or it's in nothing. And since an element can't be in nothing, it must just be in A. Okay, so that's our answer. All right. Part C is asking the same thing. Okay, so this is saying either A union B intersect with A union B complement, intersect with A complement union B complement. All right. Okay, but we already did this. Okay, so I'm not going to reinvent the wheel here, right? This was part B. So that's the same as the set A by part B. Okay, so this is really just saying A intersect with A complement union B complement, right? And now I can distribute this into both terms, and I have A intersect A complement, union, this is the overall structure, union, A intersect B complement. Okay, I think I actually made a mistake. This should just be a B. Okay, but then A intersect A complement is the empty set, and the empty set union this is just this, A intersect B. Okay, so that's the answer. So use the result of part A in order to show parts B and C. Let's move on. Okay, so this is problem 7, which says a target is made up of 10 circular disks bounded by 10 concentric circles of radii R1 through R10, where you have, all the radii have some order. Let A sub k be the event consisting of the disk of radius R sub k being hit. And they want to know what the events B and C are, where B is the union from k equals 1 to 6 of A sub k, and C is the intersection from k equals 5 to 10 of A sub k. Okay, so I'm going to go ahead and draw a picture. Okay, so we have all these concentric circles. Okay, maybe I'll just draw one more so you can see. We don't know what the radii are, it doesn't really matter, but this is going to be the first disk, and we're going to label that R sub 1. That'll be the second disk, that's R sub 2. That'll be the third disk, R sub 3, and then that's going to be R sub 4. And then and so on and so forth until you get to 10. Okay, so A sub k is the event consisting that the disk of radius R sub k is hit. Okay, so A sub 1, for instance, this is just an example. So A sub 1 means the centermost disk, the one of radius r1, is hit. Okay, so B is the event of the union from k equals 1 to 6 of A sub k. So B is equal to A1 union A2 union and so on and so forth union A6. But that's the same thing as either the disk of radius R1 gets hit or the disk of radius R2 gets hit and so on and so forth, but they're concentric. Okay, so just to give you an example, A1 or A2 means either this disk gets hit or this disk gets hit. But that's the same thing as this outermost disk just gets hit. Okay, since the event A1 is fully contained in A2. Okay, so another way to phrase that is the event A1 is fully contained in A2, which is fully contained in A3, which is fully contained in A6. So this union is really just the same as A6. Right? Now C was the intersection when k equaled 6 to 10 of the A sub k's. So remember that is going to be, I'm sorry, it was 5 to 10. So that's A5 and A6 and A7 all the way up to A sub 10. So what does that mean? Well, again, I'll draw like a little small picture. Okay, so that means, and I'm going to make this up, of course. Let's say that this was just, I don't know, maybe as an example, we'll do A3 intersect with A4, where this is radius 3, and that's radius 4. What does it mean that A3 and A4 occurs? Well, A3 is striking this one, which I'll code in that color, and A4 is striking this color. What's the intersection? When do both of those happen? Well, both of those happen whenever A3 happens. Right? So it's kind of the other way around, right? When A5 is still in A6, and so on and so forth. So if you intersect all of them, the intersection of all of them is just the smallest such set that's contained in everything else. So which set is inside all the other sets? Well, A sub 5. Because that's contained in something that's contained in something that's contained in so on and so forth until it's contained in A sub 10. So this is just A sub 5. All right, and that's problem 7. Let's move to the next problem. All right, so number 11 says that a friend forgets the last digit of a telephone number and dials the last digit at random. What is the probability of calling no more than 3 wrong numbers? And how is this probability changed if they recall the last digit is even? Now, this is the important part. Assume that your friend is smart enough to not redial any previously missed attempts. So let's say the number is, I don't know, 555-555-0155, and they knew all the number except this last digit. They're like, I don't know what that is, so I'm going to try a 0. And 0 doesn't work. They are not going to retry the 0 on the second attempt. They're going to be smart enough to choose one number from the remaining 9, and so on and so forth. Okay. Okay. So remember, this chapter is all about unions and the addition principle. So we're going to go ahead and define the event A sub k as getting the number correct, or getting the last digit correct on the kth attempt. So if you know that this is the geometric distribution, then shh, we're not there yet. But what this means is we essentially want to find the event A, which is going to be a union from k equals 1 to 4 of a sub k. Why all the way up to 4? Well, you could get it correct on the first attempt, which means you missed 0 times. Get it correct on the second attempt, meaning you missed once. The third attempt, you missed twice. And the fourth attempt means you missed 3, which you're allowed to, right? You can dial 3 wrong numbers and then get it correct on the fourth attempt. Okay? So remember the generalized inclusion-exclusion principle. Well, it turns out we don't need that because the a sub k's are mutually exclusive. You either get it correct on the first attempt or the second attempt or the third or the fourth. You can't get it correct on 2 of those attempts. Okay, so really this reduces to a sum. So I should say, should say that since, so the probability of A, which is the probability of this union, and this is of course only for mutually exclusive events, is going to equal the sum from k equals 1 to 4, the probability of each of the a sub k's. Okay, so we have to actually find each of the a sub k's. But I'm going to go ahead and claim that all the probability of a sub k's, all of them are actually going to equal 1/10. That might be counterintuitive, right? Like, if we have new information, why is the probability the same? Okay. Well, let's see. What is the probability of a sub 1? Well, by definition, the probability of something is the number of ways that that something can occur divided by the total number of outcomes. Okay, so let's just assume that there were, 10 trials. Out of those 10 trials, you're clearly just going to pick the numbers 0 through 9. There's only one way that you're getting the correct number, and there are 10 possibilities. Okay, so the probability of a sub 1 is equal to 1/10. Now it gets a little more complicated with a sub 2 because we haven't learned the multiplication rule yet, so I'm going to show you how to get around that. Okay, so in order to get around that, so for the probability of a sub 2, let the number of trials equal 100. Okay, so out of the 100 trials, which I'm going to do in a different color, so if we have 100 possible trials, we know that in 1/10 of those situations, you're going to get it correct. So 1/10 of the time, which is 10, you're going to correctly dial the number. Okay? So if that happens, this turns into a sub 1, which is just 10 over 100. Okay, but a sub 2 means, no, I actually get that wrong, which means I go down the 9/10 avenue, right? Because these are both mutually exclusive, and you either get it correct or you get it incorrect, which means 90 times you will get the incorrect number. Okay, well, if you get the incorrect number, you're going to dial again, and a sub 2 says that you get it correct one of those times. Okay, however, you are actually not multiplying by 1/10 this time, because remember, your friend is smart enough to not pick the same number twice, which means they're actually going to have 9 to choose from. So 1/9 of the time, they're going to get it correct on the second attempt, which means, again, they have 10 correct numbers and then 80 incorrect. Okay, so probability is, of course, the number of ways something occurred divided by the total. Well, again, in this situation, in a sub 2, where they get the first one incorrect and then the second one correct, that means they're looking at 10 different possibilities, 10 different ways that could happen, divided by 100 total trials. Okay, so that's why the probability of a sub 2, which is the number of ways a sub 2 can occur divided by the total number of possibilities, that's going to equal 10 over 100, which is a tenth. And if you're feeling like, well, what do you mean by 100 trials? Well, just set them up with ordered pairs if you don't believe me. Maybe the answer is 5. Maybe that is the correct digit. And maybe the first one, the first failed attempt is 0, and then they get 5 on the next time. 0, and then, or maybe 1 and then 5 on the next time. Okay, there are going to be 10 different ways out of the 100 that can occur. Okay, because it's impossible to get both, to choose the same thing, to get 0 and 0, for instance. That can't happen because your friend is smarter than that. So just by listing them out, you can get the same result. Okay, so therefore, the event A, which was the sum of these probabilities from k equals 1 to 4, but remember each of them was the same, so that's just really just going to be 4 times a tenth, which is 4 tenths or 2 fifths. Okay, and if the person knew in advance that the last digit was even, that eliminates half the total sample space. So capital N gets cut in half. Well, what happens when you divide something by a half? You really multiply by 2. So if the last digit is even, then that probability is really twice the probability of A, which is 2 times 2 fifths, which gets you 4 fifths. And that is problem 11. Let's move on. All right, so here's problem 14, very famously called the birthday paradox. But I hate when people call things a paradox when really it's just a really hard to believe result. So I call it the birthday problem. And it says to write an expression for the probability which depends on R, that among R randomly selected people, at least 2 have a common birthday. Okay, the reason that this is called a paradox is because you are only thinking about yourself when you think about this problem for the first time. So just as a quick example, just to get you interested, let R equal 10. Okay, so you have 10 people in the room. What's the probability that nobody shares a common birthday? Well, I bet that you're thinking, well, if I don't share a birthday with this person, they don't share a birthday with me, they don't share a birthday with me, well, but other people can still share a birthday with themselves. So not only, if this is you, not only do you have to rule out the possibility of you and everybody else sharing a common birthday, but you have to do the exact same thing for every single person, right? And pretty soon it becomes so networked that I'm sure it would be very easy to believe that the probability is much higher than you think. Okay, so let's kind of answer the question, and you might be surprised at the outcome. And let the event A be defined as, at least 2 individuals having a common birthday. Well, unfortunately, this is incredibly difficult to figure out, right? Because at least 2 could be 2 or 3 or 4 all the way up to R, and R could be like 100. Okay, so we're not going to do this, and instead we're only going to look at the complement and then just find the original event by subtracting the probability of the complement from 1. So what is the complement? Well, the complement is that nobody has a common birthday. And this probability isn't that bad to figure out. Okay. So how do we find the probability of that occurring? Well, let's put our thinking caps on for a second. Okay. Probability of that occurring is still going to be the number of ways that that could occur divided by the total number of ways. Okay. Well, what does it mean if nobody has a common birthday? Well, that means that out of your entire population, you find every possible pair of individuals, a set of 2 individuals. You find every such pair, and you single-handedly rule out that every single pair has a common birthday. You say, nope, this pair doesn't have a common birthday, and this pair doesn't have a common birthday, and you do that for as many pairs as there are in the R individuals. All right? Well, the question remains, so to first answer this, we should probably answer the question, how many pairs are there? How many pairs exist? How many, I should say, unique pairs exist in a population of R people? Or, reframed a different way, how many unique subpopulations, there's that word, subpopulations, many unique subpopulations of size 2 from a population of size R. You can watch one of my videos where I talk about combinations, and I can just write down the answer. So this is equivalent, or this is equal to R choose 2. Or another way of phrasing that is you take R people, and that's how many are available for the first person in the pair. And then out of that, there's going to be R minus 1 for the second pair. But doing that double counts everybody, right? Because A and B and A is counted twice when it really shouldn't be. So you actually have to divide that by 2. Okay, so for every, and this is going to be an integer. I mean, it better be an integer, right? So however many this is, we have to rule out that those individuals have a common birthday. So what is the probability that just one pair does not have a common birthday? So how about just one pair? Well, the probability that just 2 people don't share a common birthday, that's going to be 364 divided by 365. If we assume that this person's birthday is fixed, then there are, out of 365 days, and this one fixed number, there are 364 other numbers that this person could be. Other numbers that aren't person number 1's birthday. Okay? So by that, we have everything that we need. Okay? We have the number of pairs possible, number of unique pairs, and for each pair, we have the probability that they don't share a common birthday. Okay? So instead of using this formula, we can really look at it like this. I would prefer to look at it in this case. So treat this kind of like theorem 1.2, if you remember what that is. This is kind of theorem 1.2 in a way. And this is the first pair of individuals. And this is the second pair of individuals. And this is going to continue until the last pair of individuals. Well, how many pairs of individuals are there? R times R minus 1 all over 2. So that pair. And all of them have the same probability to not share a common birthday. 364 over 365. So we just multiply all of those together. And really this is alluding to something called the multiplication rule, which we'll study in chapter 3. So apologies for that, but this is really just the most straightforward way of thinking about it. So we have that the probability of the complement is really this probability multiplied by itself R times R minus 1 over 2 times. So that means that the original event A is just going to be 1 minus this probability. Okay. So what I'm going to do now is just show you a little something. So I'm going to plot this expression in Desmos. Let's just see what we get here. Okay, so what was it? 1 minus 364 over 365. And that is being raised to the power of, and now it really likes if I use x. So we're going to use x minus 1, all divided by 2. Okay, so that doesn't look very revealing, so I'm going to have to zoom out. Maybe I should zoom in a little bit. Okay, so it looks like it's increasing a little bit. And the reason that it's, I forgot to put parentheses around this. No, that's it. Okay, so obviously with more people comes more pairs, which means more of a probability of getting it correct. Okay, so you might be surprised in seeing that with just 23 individuals, we get 0.5, which means 50% likelihood that just with 23 people in a room, 2 of them share the common birthday. Now, how about for greater numbers of people? Well, clearly, I'm sure you could guess that for, say, 365 people in a room, the probability of that occurring is 1. Because all of them are either going to have different birthdays, but then the next person, the 366th person, will most definitely, by the pigeonhole principle, has to match one of the pairs. Okay, so this is actually so close to 1. This is like off by 10 to the minus 25 or something like this. But it's basically just 1. So it has a really, really high kind of exponential growth, and then it kind of just levels off. Okay? So I think I answered that. Let's move on. All right, last problem, and you can see that it's pretty difficult based on the number of stars. And it says, use the inclusion-exclusion principle in Stirling's formula to find the probability that at least one player is dealt a complete suit in a game of bridge. So remember, the way that bridge works is you have a person and their partner is sitting right across from them, and you have an opponent with their partner sitting across from them. That's basically the setup. So out of 13 cards, at least one person has 13 cards all of one type, either hearts, spades, clubs, or diamonds. Okay, so to start this problem off, we're going to go ahead and let A sub k be the event where the kth person is dealt a complete suit. And we want A to occur, which is going to be the union from k equals 1 to 4 of the A sub k's. But the A sub k's are not mutually exclusive, right? The first person could be dealt a suit and the second person could be dealt a suit. Okay, so we're going to have to use theorem 2.2 to say the following. So the probability of A is going to be equal to P1 minus P2 plus P3 minus P4. But I'm going to go ahead and go one step further and actually write out what this notation is. So the probability of A occurring is the same as P1 was the sum from, we'll say, I equals 1 to 4 of the probability of A sub I. P2 was the sum where I and j were between 1 and 4 of the probability of A sub I intersect with A sub j, plus the probability P3, I, j, and k were between 1 and 4, and that was the probability of A sub I intersect A sub j intersect A sub k, minus P4, which was I, j, k, and l, all between 1 and 4 of all these intersections. So kind of a lot. That's why it's a 3-starred problem. But let's just dive right in. So we're going to focus on P1. All right. Okay. So how do we find P1? Well, I always like to start off with the definition of probability. So the probability of A sub k is equal to the number of ways A sub k can occur divided by the total number of possible outcomes. Well, how many total possible outcomes are there in a game of bridge? Well, in a game of bridge, you are distributing 52 cards and you're giving 13 cards to each person. Okay, but since we're only really concerned with one person at that time, right? We're only concerned with one person being dealt a complete suit for A sub I. We're not intersecting it with anybody. We really just have to worry about all the different ways that you can give out 13 cards out of 52 total. So in this case, okay, so since we are only concerned with one person, okay, namely the A sub I person, the ith person, the total number of outcomes just pertaining to them is going to be 52 choose 13. We only care about the first person. We don't care about everyone else, because if they get a complete suit, good for them. That's all we need. Now, how many different ways can that occur? Well, there are 4 different suits, right? So let's say they get all 13 cards of a particular type. Well, there are 4 different suits, 4 different ways that could happen. Either they get all hearts, all diamonds, all spades, or all clubs. So there are only 4 ways of getting a complete suit. That's, of course, diamonds, spades, clubs, hearts. Okay, so that makes this ratio. Which I should be more consistent. a sub I. And that's really just going to be 4 divided by 52, choose 13. Okay, so now we are summing from I equals 1 to 4 of all of those probabilities. Okay, but the 4 people are interchangeable, right? The first person could have that happen to them, the second person, the third person, or the fourth person. It has the same probability for each person to have that happen to them, which means when we're really taking the sum of all of these, we're really just multiplying it by 4. Okay, or another way of phrasing that is from 4 individuals, we're choosing 1 person for that to happen to. So it's really 4 choose 1 of 4 divided by 52 choose 13. Okay, so that is P1. The other ones are going to be kind of similar. It's a similar idea. All right, let's do P2. And remember, we are subtracting it, but let's just find P2 for now. And that's this term. So now we're summing up all the different double intersections. Okay, so P2. Okay, now we're trying to find the probability of a sub I intersect with a sub j, and then we'll sum it up later. But remember, this is the number of ways that a sub I and a sub j could occur, divided by the total number of possible outcomes. Okay, well, the total number of possible outcomes is going to change now. Okay, why is it going to change? Well, we have the same 52 choose 13 from before. Okay. But then however many ways that can occur, after one suit is dealt, right? We're assuming one suit has to be dealt for a sub I and a sub j to occur. So after this happens, how many cards are left over? Well, if you have 52 total cards and 13 of them already belong to one of the players, then you're going to have 39 total cards to choose from. And then that 39 cards can be divvied up however. Okay, but in order for a sub I and a sub j to occur at all, this has to happen. So this is one person has a suit. And then after that, it doesn't really matter. So how many ways are there from the remaining 39 cards? We're choosing 13 of them to give out to the other players. Okay, but this has to happen in this case. So that's why this is the capital N. Okay, and how many different ways can a sub I and a sub j occur? Let's think about that for a second. This is the ith person, and this is the jth person. Well, there are 4 different suits for the ith person, and after that 4 suits, if they have one of them, the jth person only has 3 possible suits to choose from. So we have 12 possibilities there. Okay, so if we're trying to sum, where I and j are between 1 and 4, of the probability of a sub I intersect a sub j, now that's going to be a sum where I and j are between 1 and 4 of 12 divided by 52 choose 13 times 39 choose 13. Okay. Now, this number was calculated by looking at the number of possible ways that any two people, can get a complete suit. This person has a possibility of 4, and this person has a possibility of just 3. Well, how many different sets of 2 people are there in the game of bridge? Because we're summing over all of those possibilities. Again, each pair has the same likeliness to occur. So we just have to calculate how many subpopulations of size 2 there are in the 4 players of bridge. Okay, well, that's just going to be kind of like before. It's going to be 4 choose 2. Or you can just like enumerate all of them, right? If you have, 4 players, it could either be this one and this one, 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 this one and this one. Okay, so that's 6. 4 choose 2 is also 6. So you get the same thing. Or it's going to be that times 12 divided by 50 choose 13 times 39 choose 13. Okay, see if you can do P3 on your own based on everything that I just did. Okay, I don't want to kind of go through this again, but I guess I can do it one more time. Okay, I have to figure out what to shade it in. Oh, let's do it in this color. So now we're going to find all of the sum of all the triple intersections. Okay, and that's going to be P3. Whoops. All right, so for P3, all right, again, we have the probability a sub I intersect a sub j intersect a sub k is the number of ways that could happen divided by the total number of possibilities. Okay, well, the total number of possibilities in a way is kind of forced, okay, because you have the 50 choose 13, okay, for the first suit, and then from the remaining 39 cards, you're choosing 13 of them, and then from the remaining 26 cards, now you're also choosing 13. Okay, another way you can think about this that's the same exact thing, and I guess I'll show it here. You could also think about it like the following. If I'm only looking at situations, in which a sub I, a sub j, and a sub k could possibly be dealt a complete suit, that means I'm dividing 52 cards up into groups of you're dividing it up into possibilities of 13, 13, and 26. Okay, 13 because that's the first person that's guaranteed to have a complete suit. 13 because the second person is also guaranteed to have a complete suit. And then we don't know if the third person also has a complete suit or not. That's what this probability is designed to figure out. So there are 26 remaining cards to divvy up between the 2 individuals. Okay, so this, by the partitions formula, is 52 factorial divided by 13 factorial, 13 factorial, 26 factorial. And if you work this out and you simplify terms, I believe you will get the exact same thing, right? So you should do that as an exercise. But then how many ways can AI, AJ, and AK occur? Well, it's going to be 4 times 3 times 2. Okay, 4 suits for the first person, 3 suits for the second person, 2 for the third person, which means if you're now summing over I, J, and K being between 1 and 4, okay, what is that going to be? Well, if I, j, and k are between 1 and 4, how many different triples are there? Well, that's going to be 4 choose 3 times this, which is 24, divided by 52 choose 13, 39 choose 13, 26 choose 13. Okay, and you should work out for yourself that P4 is 4 choose 4 times 24 divided by 52 choose 13, 39 choose 13, 26 choose 13, and then after that, then the remaining 13 cards are essentially dealt 13 people. So this term is basically 1, which means these have a common denominator, by the way, which is going to be important when you start simplifying this. Okay. So let's put it all together. We get that the probability of A occurring, I guess I should do this in a different color. So the probability of A occurring is P1 minus P2 plus P3 minus P4, which is going to equal 16 over 52 choose 13 minus 72 divided by 52 choose 13, 39 choose 13, plus 96 divided by 52 choose 13, 39 choose 13, 26 choose 13, minus 24 times 52 choose 13, 39, I almost wrote that as a fraction, I apologize. 39 choose 13, 26 choose 13, 13 choose 13. All right, but 13 choose 13 is 1, which means I can actually just combine these and write them as a single term. 96 minus 24, that's 72. So I'm actually just going to combine these so I don't have to write this again, because I do not want to write this again. That's what I get. That is my exact answer. Unfortunately, exact isn't so good because we have a lot of factorials in here. Okay. So it turns out that when you simplify all of this, you're going to have 3 terms. And it turns out that this term is the most significant term. So I'll leave it up to you to kind of finish that out and use Stirling's formula in order to approximate the orders of magnitudes of all of these terms. And when I did it, I believe I got around on the order of 10 to the minus 11 for this term. I got on the order of 10 to the minus 20 for this term. And I got on the order of 10 to the minus 28 for this term. So clearly these don't matter, and this is the only term that really matters. And when you actually do the simplifying here and use Stirling's formula, you get approximately 2.5 times 10 to the minus 11, which is 1 in 100 billion, which means it's probably not going to happen, even if we lift up the restrictions so that at least one person gets it. Probably not happening. All right, this was me reviewing a little bit of Chapter 2. If you have any questions over any of the exercises, let me know. Otherwise, I'll see you in Chapter 3.